So I am going to attempt to answer an old question here that had to do with the assignment where you were doing number 75 out of chapter 14. 75 said calculate the percent dissociation of the acid in each of the following solutions, and letter C was a solution of 0.0050 molar acetic acid. So I'm going to pop over here to the solutions and see if I can't explain this a little bit better. So here's the solution to 75C. They've got the Ka expression, which would have been given to you, and this was their equilibrium set up after they would have done an ice table. And remember, when you're calculating percent dissociation, you're essentially just trying to figure out how much of it will separate, right? How much will be hydrogen ion versus how much will stay together. So they did the 5% rule here. That's where we got rid of the minus x, and all of a sudden it's 0.050. And when you check the assumption, you check the 5% rule, you actually find out that it's greater than 5%, which means our 5% rule cannot work. So they said we should solve exactly. Now, one process is what's called successive approximations. We would have just done the quadratic formula. Okay, so anytime where you see successive approximations, this is essentially saying that, oh, our shortcut didn't work, so we also could have done the quadratic formula. If you did the quadratic formula or you understand the successive approximations, don't worry about spending time trying to figure it out unless you already have. Essentially, you then figure out that your x value is 2.9 times 10 to the negative fourth. So that would be my how much hydrogen ion and how much anion I would generate. Now that I have an actual x value, then I can come down and actually calculate my percent dissociation. I think the questions that I kept getting, so once I knew my x is 2.9 times 10 to the negative fourth, we divide that over the original concentration, which was 0.0050 or 5.0 times 10 to the negative 3. We get 5.8% dissociated. Now, I realize it looks like these x values were not far off, and you're right, but they're far enough off. And so the 5.8% dissociation is far enough off that we have to do the extra math. So the reason it looks different is because we had to, essentially, when we did our 5% rule, it didn't work. So we then had to do some ugly algebra to get there, okay? If that's the only one you're stuck on, I wouldn't worry too much about it. I think you're headed in the right direction. This just had a wrinkle for algebra. And remember, now you won't take a formal official test from me probably on this unit, but even on the AP test, they're probably not going to waste time for you doing the quadratic formula. So this would be an algebra hiccup, I think. All right, the other question, Abby, that I believe that you had is this part down here about why when acids are diluted, the equilibrium shifts to the side with more particles. The best advice that I can give to you is this is really similar to changing the volume of a system and it's shifting towards more gas particles. If we add more water, okay, if we add more water in, I'm going to pull up PHET sim. Nope, not going to do that. If I add more water into a situation, I essentially give the ion pieces more room to move around. So when I add more water and there's more room to move around, they're going to shift to the side that has more opportunities for movement or more ions, which is why more of it will dissociate. I could do a little bit more on that, so I'm going to start there to answer those questions. If you guys still have questions, follow up. We'll get it figured out, and I'll try to answer them as best I can. So, talk to you guys soon. Bye-bye.